Reint Fischer, who are working on tracking, using Lagrangian tracking to study the dispersion of microplastics into the ocean and the processes that affect that. Microplastics in the ocean, as you know, is one of the biggest problems of ocean pollution. Governments are trying to find ways to address this issue, but we don't really know a lot of important elements of their transport, of how they interact with the environment and what the effect they have. Even we don't even know how big sometimes these patches of ocean pollution are. Delphine Lobelle is a postdoctoral researcher at Utrecht University, the Institute of Marine and Atmospheric Research. She completed her PhD at the University of Southampton in 2019 using CMIP5 models and observations to investigate trends and variability of the past and future overturning Atlantic meridional overturning circulation. She's now working on the global Lagrangian 3D transport of microplastic affected by algal attachment or biofouling. Reint Fischer is a research assistant at the same institute in Utrecht, and he has completed the master's in climate physics with his research on Lagrangian connectivity within coral canopies. Aside from the research on microplastic biofouling, he is involved in the community development of Parcels and is interested in scientific visualization. Starting this September, he will come to the US and he will enroll in the University of Maryland, the graduate school program at the Department of Atmospheric and Oceanic Sciences. And with that, I will give the floor to Delphine to start her talk.
Great, thanks. Thank you so much for hosting and thanks for inviting us. We're really excited to be here and show you our work. And firstly, I would just like to see that the screen is sharing okay and that you can hear me. I know we tested it, but just to make sure.
Yeah, this looks great. Thanks.
Perfect. So we know that this is your lunch talk and it's supposed to be informal. So we're trying to have a lot of cool animations to show you, and we'll start off with a video. And I'll really explain a little bit about the Lagrangian particle tracking side of things and what we're doing with our simulations. And then Reint will show some of our first results and explain to you why we're presenting today, because we're looking at the NASA GISS data and seeing if we can use those fields for our simulations. So what you see here, the animation, so it just started again, and we release particles in the Southern Ocean at the surface, and here you see that the particles are moving with advection, with mixing, and we're also including biofouling. So biofouling is algal attachment on the surface of a substrate, and in this case, our particles are plastic, microplastic. You see that we're using two different sizes, 1 millimeter and 10 micrometers. And these particles are moving up and down in the vertical. So here the color bar is showing the depth. And so that is what we're going to be explaining today, how these dynamics affect the 3D transport, so the biological and physical interactions with particles, and how that can affect the 3D transport of these particles. So this is, it's important to say that this is work that is with a lot of co-authors, some that are in the Netherlands at Wageningen University, others that are in Switzerland. Also, Linda is also in the Netherlands at the Royal Institute for Sea Research, and others that are in the UK. So, okay. So we would like to start off with a video, because we realize that a lot of you maybe don't know much about plastic research. So a very cool video just came up on YouTube. It's a Vox video, and our boss Eric van Sabeel was interviewed for this, and our Twitter page, You Follow the Ocean, is also featured. So you can try to see when Reint's awesome simulations are coming up. So just let me know.
Between Hawaii and California, in an area about twice the size of Texas, is the Great Pacific Garbage Patch. For decades, tons of our plastic debris has accumulated there because of swirling ocean currents. It looks like a cloudy soup, and that's because the plastic objects are spaced far apart, and they range in size from large debris to microscopic. There are at least 4 other garbage patches like this in the world. And after scientists discovered them, starting in the 90s, they thought that this might be where a lot of the plastic ended up, out there, floating on the surface. But recently, scientists brought large nets to the Great Pacific Garbage Patch and took a closer look at the objects they pulled out. They found water bottles and hard hats and bottle caps and toothbrushes and toilet seats and laundry baskets. And using what they found, they were able to calculate how much debris was in all of the garbage patches.
There were about 300,000 tons of plastics at the surface of the ocean, which is a huge number.
It is a big number, but a few 100,000 metric tons of plastic is only about 1% of the estimated 8 million tons of plastic scientists believe is emitted into the ocean every year. So scientists have been left investigating a mystery. Where does the rest of the ocean's plastic go? This is clue number 1 in the case of the missing plastic, a seafloor sediment sample. It was taken from the bottom of the Santa Barbara Basin off the coast of California. It represents a measure of time from 1870 at its deepest layer of sediment up until 2009. But this period from 1945 to 2009 is where the study authors were focused on. It's the era of plastic production. In these layers, scientists found plastic fibers and fragments that were 1 millimeter or smaller in size. They found more and more plastic particles as the years went on, doubling every 15 years. That rate is nearly identical to the rate of global plastic production.
As soon as you see a layer of microplastic, you know you passed the 1950s. And that's the legacy of our generation.
This is Laurent Le Breton. He works at the Ocean Cleanup and led the study of the objects in the Great Pacific Garbage Patch.
And this will be there forever. We know that.
The sea sediment study looked at microplastics, particles smaller than 5 millimeters. These either come from synthetic clothing fibers, or they are the result of larger plastics breaking down. We found these tiny particles floating throughout the ocean, and even in the guts of the ocean's tiniest creatures, like plankton. But the sediment study shows that some of our plastic is likely hiding, buried in the seafloor, too. But here's another clue. This is a plastic bag captured 2,500 meters below the surface of the Arctic deep sea. It's one of over 2,100 photographs taken with this deep sea camera.
Part of the work that we're doing is to look at the impact of climate change in the Arctic. We use towed camera surveys to look at the impact on large animals like starfish and snails, sponges. And while I was doing these surveys, I saw that more and more plastic debris was on the seafloor.
Melanie Bergman's research shows that large plastic objects don't just float on the surface or degrade into microplastic. Some of them sink without breaking down. One study found that about 50% of plastic in landfills is more dense than seawater, which means these objects could sink on their own.
But even those other 50% may actually travel to the seafloor with time. Debris which is floating on the ocean surface becomes colonized with barnacles, mussels, all sorts of different organisms. And then it becomes heavier and heavier, and at a certain point it then starts to sink.
Bergman's research is difficult to replicate throughout the ocean because of the challenge of surveying deep sea environments. But it suggests that some of that missing plastic might be sitting on the seafloor, intact. Another clue complicates the mystery, though. This plastic crate from Taiwan. It's one of the objects excavated during the harvest in the Great Pacific Garbage Patch. And what struck researchers was its production date, 1971. When they looked at the production dates of other objects, they saw a trend. A lot of it was old trash. This was a new lead. Because if the majority of plastic pollution degraded into microplastic or fell to the ocean floor, then what you'd see in garbage patches would be new plastic.
And that changed the story because the plastic that is accumulated at the surface of the ocean is actually very persistent. The plastic we find in subtropical oceans may actually be there for decades, if not centuries.
It turns out the new plastic is far closer than the open ocean or the bottom of the deep sea. Le Breton's research found that plastic objects on coastlines have more recent production dates than plastic in the open ocean. This clue led scientists to think a lot of debris actually stays close to shorelines around the world, hidden in plain sight.
Some of that will end up in the middle of the ocean in garbage patch, but actually a lot of it stays fairly near shore and hops from beach to beach to beach.
Eric van Sabeel is an oceanographer and is building an ocean model that predicts where our missing plastic ends up. The completed model will be finished in 2022, but in the meantime, he and his team published initial results to a Twitter feed.
We use simulations of the ocean currents, and then we put in virtual plastic. We move that plastic with the ocean flow. At the same time, the plastic can fragment, it can degrade, organisms start growing on it, and that weighs down the plastic so that it slowly starts to sink into the deeper ocean. So in that way, we're doing like this gigantic simulation of all of the ocean, of all the plastic moving around.
Van Sabeel thinks that a majority of plastic pollution is within 100 miles of shorelines, continually getting washed back up on beaches, down coastlines, or up and down to the sea floor.
Plastic continuously goes back and forth between the coastline and offshore. That's a lot of rubbing and fragmenting and scraping over the sand.
This commotion helps explain the presence of microplastics in sediments and animal guts too. Laurent's organization is working on cleaning up the garbage patches in the middle of the ocean, but that won't do much for the other 99% of our plastic. The microplastics becoming part of our food web and geologic record, the larger debris sinking to the bottom of the ocean, and more likely than not, the stuff getting washed up on beaches. Like this one, where I recently visited, where I found a mix of micro and larger plastics. But knowing where plastics end up can help us keep this plastic heap from growing. These photos were taken by volunteers at an annual International Coastal Cleanup event organized by the Ocean Conservancy, where people volunteer to pick up plastic on the beaches near them. The most common objects they find are food wrappers, cigarette butts, plastic bottle caps, and plastic cups and plates. The easiest way to get plastic like this out of the ocean is to prevent it from entering in the first place, with better recycling programs, or producing and using less plastic altogether. There are nearly 400,000 miles of coastline around the world, not all of it accessible for people. But knowing that most of our plastic pollution hangs out along shorelines before it becomes microplastics or floats out to the open sea means beach cleanups can go a long way in preventing further damage. So if you see plastic pollution on a beach, all the more reason to pick it up.
Okay, so
between Hawaii and California.
There we go. So yeah, hopefully that gives you an overview of what's our research, you know, the big picture of our research, and really what our team is trying to answer is, where is all the ocean plastic, right? So there are estimates of how much of that plastic actually enters the oceans. And then now we're really trying to simulate, okay, how much of that is actually beached, how much of it ends up in sinking down the water column. So as one of the first papers that Eric published about all of this missing plastic, this 99% of missing plastic, is this paper in 2015, showing that there is a lot of accumulation that happens in these convergence zones in subtropical gyres. And so you saw those in the video too. And basically the amount that is at the surface is only 1% of what is estimated to be entering the oceans annually. And so that really shows that we have this question that is, where is all the rest of the plastic? And so we have this European Research Council grant that is until next year, and it's called Tracking of Plastic in Our Seas. You can check out our website if you're interested in the different projects that the postdocs and PhD students are doing. So how is this plastic actually transported around the ocean? Well, there are lots of physical processes that can interact with the plastic, and it really depends on the scale and the location of where this plastic ends up. So on the coast, you can imagine there's a lot of wave interaction. In the open ocean, there's Ekman transport, Langmuir circulations, all types of different things that different people in our group are looking at. And when it comes to biological interactions, there are also a variety of different processes. And the one that we are focusing on is this biofouling. Since it's been shown that the increase of density of these particles can really impact the 3D transport of the microplastic. So this is really the aim of our study. It's modeling the effects of biofouling, the algal attachment on the microplastic, and seeing the effects of this on the 3D transports of the plastic in the ocean. And we are really trying to simulate these physical and biological interactions as best as possible with the current models that we have. So the motivation behind why we started looking at these processes was this paper in 2017 that was published by Kooi et al. And they were looking at these potential oscillations that can happen of microplastic in the ocean. So here on the x-axis is the time in days, and depth is on the y-axis. And they created this 1D idealized model of biofouling. So basically the interaction, the collision of algae with microplastic, then the growth of that algae on the surface, and causing the particle and the biofilm to sink due to an increase in density, and it being a larger density than the surrounding seawater. And once that particle reaches a depth where there are no longer the conditions for growth of algae, it falls off, and this buoyant particle can then resurface back to the surface, and then the process happens again. So this causes oscillations in the water column. And so we wanted to take this model and to produce a 3D version of it to see whether, when we include advection and mixing, what happens to whether these oscillations still occur, and to take it onto a global scale. So instead of it just being at one location, really seeing how different regions are also affected. I see there's a question. Is this yeah? It just popped up on my screen, but
should we leave it for later?
Yeah.
As you wish.
Okay.
You can address it whenever you want, Natasha, if you want.
Okay, well, I can just pop it up and check it out. So what's the role of downward migration in the vertical transport of microplastics? So yeah, that's a good question. And we're actually going to explain a lot of the biological components that we're including in the model. But since we're using outputs from the model's simulations, such as the Euromodel, the NASA GISS one, but you know, we're going to show you another model that we're using first. But yeah, some of these really kind of, because a lot of the models are on, for example, 5-day averages, then you will no longer have these vertical migrations simulated within those models. But yeah, maybe this will become more clear once we explain the methods section. Right. So yeah, what is required for the setup of our simulations? So we do these Lagrangian simulations, and so the Lagrangian framework is using this OceanParcels tool, and I'll explain a bit more detail about it in a bit. And for the field set data, for the hydrodynamic and the biogeochemical data that we require, we use an ocean general circulation model. And for now, that model that we're using is this NEMO-MEDUSA 2.0. So what is a Lagrangian analysis? Just to give a very brief introduction. So Lagrangian oceanography is really looking at the connectivity in the ocean and how water actually moves around from one place to another, how long it takes, and what we can actually use this for is the transport of different elements such as water and traces. Like it's very important for climate change too. Microorganisms, litter, icebergs, fish. So there's a long list of different projects that can actually use Lagrangian particle tracking. And it can also be used to understand ocean dynamics. One of the key things that is actually very useful, especially for us looking at ocean plastic, which is really hard to actually collect samples of this in the open ocean. And on a global scale, it's really, really challenging. So that's where these virtual simulations come in really handy, because we can really release millions of particles and see where they end up. So OceanParcels is this Lagrangian particle tracking tool that we use. And so Parcels stands for probably a really computationally efficient Lagrangian simulator. And it was developed by Eric and others a good few years back. It's an open access code. So it's on GitHub. You can go onto this GitHub page, and there's lots of people have contributed in the past to the development of the code. And as you see here, throughout time from 2015, there's really been a lot of different people contributing. And one of the great things is it's very easy to use. So there are lots of tutorials, and our team is always happy to help anyone who would like to use the tool. So if you're interested, and then please do get in contact with us and look at the website for more information. And so OceanParcels is very flexible, right? So it's generated with the simulations are set up with Python classes, which are customizable, and so you can really choose what behavior you would like to give to your particles. Both passive and active particles can be tracked, and so by that, it can be water and plankton, even plastic, if you want it to just follow the advection. And for active particles, you can go from anything from Argo floats through to fish. So you can really encode whatever you would like for your simulations. Here I've given a few examples of sinking, swimming, fragmenting of the particles, for example. And so then the way that the simulations are set up, you need to input the fields from an ocean general circulation model. And so then these fields are interpolated to a specific point that you can define, and then the particles are integrated through time in order to give these full trajectories. And here's just a schematic to give an example of, as the user, you can really define within what are called kernels, the code to give particles a particular behavior. And also any ocean general circulation models can be used in theory. And so just to give a brief overview of the advective algorithm that's used, this X term is the 3D position of a particle. And so that's at time t plus delta c. So you can really decide how long you want between each of your time steps for your simulations. And here the v is the 3D velocity field at a particular location. And this final term is what I was just mentioning about this behavior of the plastic. So in our case, to give an example, it's both biofouling, and we're also looking at the effects of mixing. So yeah, this is basically how a particle moves from one time step to the next, where its 3D location is, and then you get a full trajectory depending on how long you run your simulations. So these are some of the outputs that we are actually getting from the OGCM, which is NEMO-MEDUSA for the most part of what we're doing so far. And so there are two main components that we're using for both physical and biological interactions of the particles with algal cells. And so for the physical components, we use the 3D velocity fields, temperature and salinity profiles, the vertical diffusion, and the mixed layer depth. And for the biological, we're only using diatoms, so diatom phytoplankton for now to represent the biofilm. And we'll show in a little bit how this is one of the key assumptions in our work. And in order to simulate how that biofilm is growing and dying, we need to have the growth and the grazing, as well as other death of the diatom of the algae, other than grazing, which can be, for example, respiration, metabolism.
Hi, Delphine.
Yeah.
Hi, I just have one quick question about the mixing. I think it was about 2 slides ago. So is that explicit or that's parameterized in this?
So this is something that you can really, it's either something that is already in the model, so you can just place it as you have advection plus mixing, for example, or if you want to simulate it and you really want to compute it at each time step, then you can do so also. So it really depends on the data that you have. And you'll see that actually what we've done is a bit of both, because for the NASA GISS outputs, there is this vertical diffusivity term, whereas for the NEMO-MEDUSA, we didn't have that explicitly, so we are actually computing it. And so, yeah, that's one of the main things that Heinz is going to explain in the methods. Yeah.
But also there is mesoscale mixing, for example. Where is that included?
Yeah, that's a good question. So I guess depending on the resolution of the model, you would have some of that which is within the advection, for example. So yeah, this is something that yeah, I think depends on the model, yeah, and the resolution.
Mm-hmm. Great, you want to say something?
Okay, should I go on?
Yep.
Yeah. Okay, so yeah, so here we. Yeah, I just wanted to mention that a paper has already been published about a month ago on the first results that we had. So I just wanted to show, and let me know if you can actually see this. But this is something that I put together for a conference, the EGU conference that was a couple of weeks ago. So I thought it would be a great overview so that you don't have to read the full paper. But so the method here really shows that the biofilm on the plastic is dependent on the collision plus the growth of the collision of the algal cells on the plastic, plus the growth. And then the way that it's the biofilm dies is through grazing and respiration. And the particle velocity is dependent on the difference in density between the seawater and the particle. And it's also dependent on the initial buoyancy, so the size and the density of the particle that we're releasing. So here are some of the results. One of the key things that we found is that these subtropical gyres pop up again, but as a region where within these regions, the particles do not sink within 90 days of the simulations. So you see that there are these black regions, and that basically means that the sinking has not occurred yet. And that's because in the oligotrophic gyres, you have very low algal concentrations. So here you see it in the surface algae, that there is very low concentration here, which means that there's less interaction with the particles, and the sinking takes a lot longer. We also were looking at the effect of different sizes on the sinking of the particles. And so for the smaller sizes, the particles sink almost immediately everywhere around the globe, since very little algae is required, attachment is required for it to start sinking and increase the density of the particle. So yeah, this is where we were really zooming into two regions, the North Pacific subtropical gyre and the Equatorial Pacific. And this was part of the motivation for the work that we're currently doing with Heinz. So yeah, I think those are the main take home messages. And now I can go back here.
Sorry, Delphine, I just have one quick question. Sorry. It gets to this point of mixing. You showed kind of nicely this kind of sinking time scale. So presumably that's some kind of advective time scale, but one might think that mixing might kind of create a distribution of times. Do you have a sense of how mixing, kind of affects the extent to which there's the kind of this one characteristic time scale? Presumably that's an average, right? That you
so one important thing to state about this first paper is we didn't include mixing. So it was really just advection.
Okay.
It was immediate advection plus biofouling. And that's why we really wanted to look at mixing in our work right now. So this is definitely what you're going to see from the results of our latest results. Yeah.
Thank you.
Yeah, no worries. So this is what I'm actually just saying here. So the physical components that we're including and how we're expanding from paper one is to include the mixing. And so we've actually computed this from the wind fields from Medusa. And we've also included a background tidal mixing. As for the biological components, we've improved the biofilm behavior, and we won't go into too much detail about that, but we thought that one of the key assumptions from the Kooi model, this 1D model that I explained at the beginning, is that if the particle sinks and the algae dies, then it just falls off and can cause the particle to resurface. And we're looking into the effects of, whether there's something that remains, some of the dead material that remains attached to the particle and can still affect the density. So
Delphine, sorry to interrupt yet again. So we have one comment, which was if you could provide a reference for this paper, and then my apologies, Ron. I'm not sure how long you've had your hand raised. Did you want to? Oh, I see now it's kind of lower. Do you have a comment that you wanted to make?
Yeah, thanks. Sorry, I was struggling with the raise hand mechanism, so it's my fault. So I just wanted to follow up on your question, actually, because because the flow is unsteady, you could also get a range of mixing timescales. And so I just was, I guess, asking like how, if you looked how large that effect is, because I think Clara is right. With mixing, you're going to get a range of timescales, but just because the flow is unsteady, which I think is in your model, even if there's no mixing, you can still get a range of timescales. So I just wanted to ask about that.
Yeah, so I think most of the mixing questions, I think it will make a bit more sense once we actually show the equations that we're using for it. But it's true that we're limited to whatever time and horizontal resolution we have of the output files, right? So even if we're computing the wind mixing, for example, that's really and that OceanParcels can interpolate whatever is not within the that resolution. We are still using these output files, and so whatever we can simulate with regards to mixing is dependent on that time and spatial resolution. Yeah, but yeah, I think. Go ahead.
Sorry, I just want to make the point that you have mixing where you're trying to represent circulations that you can't resolve, but then you also have the resolved circulation, which is unsteady. And so you can imagine that if you put a parcel in the water at one particular time when the circulation is in one direction, but then the the direction of the circulation changes because of an eddy or something like that, putting a particle in at a later time may actually have, it may go off in a different direction initially. So I think that's all I was asking about. This is really kind of independent of what you do for mixing.
Yeah. I think once Heinz explains, what we've been doing with that component, it will make a bit more sense. Yeah. So let's see if your questions are answered in the next few slides.
Okay. Thank you.
Yeah, no worries. Okay, and so the last part that we've expanded on from the first paper is that we're zooming into these regions that I showed in the other presentation, and so we're now focusing on 3 different regions that have 3 very different biological and physical dynamics. And we release 10,000 particles, so we have a lot more particles. We have a higher resolution of this release location, so that we can really try to see these finer scale features and really compare 3 very different regions. And so now I'm actually going to hand over to Heinz, and he's going to explain hopefully a lot of those questions that you guys had about the mixing and yeah. So let me stop sharing, and now Heinz will take over.
Yeah, thank you, Delphine. I hope you can all hear clearly.
Yeah, it's fine.
Yes.
All right.
Great. Sorry, just before you start, we do have one question that surfaced in the chat. Matteo, would you like to ask that, or?
Well, it was, I can just read it, but we have a separately funded project. We are looking at microplastics from a more remote sensing point of view. Regarding biofilms, do you have any metrics as to what extent they affect the ocean surface refractive index?
Wow, that is a very good question. We really have not looked at that at all. So I would have to see if someone else in our team has been looking at that. But yeah, for now I don't have an answer to that.
That data is sparse, and as you know, the refractive index is a parameter that everybody knows. It will be extremely precious, but we have currently work undergoing, so hopefully I see a lot of work being done, progressively speaking, in this field. So hopefully we will get more and more field work also, right? With basic optical parameters being determined.
Mm-hmm. Yeah. Well, I will save your question and ask around.
Right.
Thank you.
Yeah, thank you. So one of the important things that has already been asked about and that we've been looking at is especially the unresolved vertical motions. So when we're talking about mixing, at the moment we are just parameterizing only the vertical motions and not the unresolved horizontal motions, and especially to look at. Especially since we're interested in this vertical position of these microplastics at the moment, so that's what we've started out with, and then of course these vertical motions are the vertical turbulence is unresolved in most cases, and so how we try to capture the range of the possible vertical trajectories for these microplastics. It's through a random walk, a Markov zero model, where we stochastically displace these particles with a magnitude related to the vertical diffusivity at that location. And then here you can see how when we start the simulation, so this is over the first 30 minutes of a simulation, particles get moved stochastically, and the large particles are buoyant enough to immediately rise back up to the surface, whereas the smallest particles get affected a lot by this unresolved vertical mixing, and therefore start moving down into the water column. And if we talk about this vertical diffusivity field, it's used in many ocean models, and the Model E output that we've gotten from Natasha includes this vertical diffusivity field. So that makes it quite easy to simulate this stochastically. And then for our other data that we use, mostly the vertical diffusivity is not included. So we calculated using the K-profile parameterization. And to give you an indication here, this is what a K-profile parameterization would look like for typical wind speeds of around 5 meters per second and a mixed layer depth of 20 meters, as you can see here. And then the improvements that we've made for the biology in the model come from also this MEDUSA model here. So in the previous paper, many assumptions were made about, and the growth of the biofilm was very simplistic. So here we have the algal biofilm that is attached to our microplastic particles, and that can grow due to collisions with ambient algae, and it can grow in regions where primary productivity is in the model output. And then there were linear assumptions made for the grazing and the respiration. And now we realize that some models also include many of these processes, and yeah, we want to try to get a better idea of how this biofilm dynamics work. And in the MEDUSA model, those include the primary productivity of specifically diatoms, the actual grazing due to zooplankton, mesozooplankton, and then some linear losses and nonlinear losses that estimate certain processes, and that includes, for example, diseases, but also respiration. And this is, yeah, these are a bit more sophisticated than what we've used before. And then, so an important assumption to realize is that at the moment we don't know too much about these specific the biofilm dynamics that happen out there in the ocean. So many of the assumptions we make are based on what the ambient diatoms currently do. And yeah, one of the points we'll touch upon later is that diatoms are of course not the only algae and the only organisms that do biofouling. But this is, yeah, within the current model capacity, this is what we can do, and this is also why we contacted Natasha for the Model E output, since there the terms included are even a bit different again. So then I would like to show you some of our first results, and we're not very far in the analysis part yet, but here I show two animations of particles released in the Southern Ocean. So this is again the same simulation as you saw in the beginning, and now with the background there's a surface diatom concentration, and what you can see again here is that the depth of the particles is shown by this red color bar. And so what's interesting here already, we can see this NEMO-MEDUSA model is at a relatively high horizontal resolution, and that captures some of the mesoscale variability. And the Model E output that we've looked at does not include that. And I must note here that for the Model E output, we have been looking at the specific terms for the biofilm dynamics, but we're a bit unsure yet if we've done that correctly. But this is just an indication of what kind of processes we can find here, and what kind of results. And then so in the end, we're interested in the vertical distribution of the particles of different sizes. And this is also due to the fact that some of the smallest particles are hardly found at the surface of the ocean. And we kind of find here two regimes. So here we've plotted the particle positions and their depth over the days of the simulation. So we've started out with 3-month simulations, starting from the 1st of January in 2004 in all these models. And here the color shows the size of the particles. So the whitest particles are those of 1 millimeter, and the most purple are of 10 micrometers. And what you cannot see very well here, but in the beginning, in the first 8 days in the Equatorial Pacific, many of the small particles, again, bounce around in the mixed layer, or potentially move around in the mixed layer due to unresolved vertical mixing. And then after a certain number of days, the particles have accumulated enough biofilm that they start sinking. And then you can see the largest particles, they start sinking first. And they, at the moment in our current simulations, they reach quite significant depths. So that's interesting to see. And one of the things that we're still developing hypotheses about is what happens to the actual diatom dynamics within the deeper water column. And there are some assumptions that we can make, of course, and we're not 100% sure yet if the biofilm would at some point fall off, or the loss terms, at least for most of the diatoms, are not so well defined within this part of the water column. And then what we can see is that in the Equatorial Pacific there are many algae, so the particles start sinking early. As we move to regions where there's less surface algae and less primary productivity, also because in the beginning especially the concentration of algae is important, but later especially the primary productivity becomes important for the growth of this biofilm, then it takes longer for these particles to start sinking. And then one of the characteristic features that we have at the moment is that once, of course, the biofilm stops growing and only starts decreasing and dying, then you get these oscillations where the oscillations of the large particles have a duration of about several days, 5 to 10 days, and the smaller the particle, the longer this oscillation will take. And then we're interested in what are then in the different regions, what are the dominant processes to vertically displace the microplastics. So here we've looked at all the observations of all the particles, and at each observation looked, okay, what is the vertical contribution due to the unresolved mixing? What is the vertical velocity due to the potential settling velocity due to the density of this biofilm and plastic combined? And what is the model advection? What's that magnitude? And here you can see on the x-axis are the orders of magnitude of these velocities. And then here on the y-axis you can see the fraction of the observations of all these particles that have this order of magnitude, where negative velocities are rising velocities and positive velocities are sinking velocities. So I'll start here. So we've divided this in what happens above the mixed layer or depth, or within the mixed layer, and what happens below. And we've looked at these different size classes. So for the small particles, as we've seen already a bit, they are very subject to the unresolved vertical motions, and their buoyancy is not as large as to be able to overcome this. So even though when the smallest particles have relatively small biofilm, then their positive buoyancy is not enough to overcome these other vertical velocities. Whereas for the larger particles, you can see that the buoyancy is enough to keep them afloat at the surface, at least in the beginning, and once they start accumulating biofilm, also they can start sinking at some point. And then if we look at below the mixed layer, then the vertical, the unresolved vertical mixing, is a lot smaller, and then you can see that especially the density dependent settling velocity becomes really important to determine the dynamics of the vertical position of these particles. So then we have some ideas on how to further use these this study and what we would like to include and propose to people to work on maybe and to have some ideas. And one is that these collisions and the unresolved part of our model, that of course there's lots of complexity in this, and some of the co-authors that we've been working with also look at smaller scales what happens. So, for example, you can imagine that that the diatoms and the plastic particles, they might be subject to the same smaller scale motions and therefore become trapped in similar locations within this smaller scale, and therefore collide more or less. One of the biological points that we've touched upon already is that diatoms are not, of course, the only colonizers. Currently we're looking at diatoms because they do play an important role, but also because they are available in the ocean models. That's something where the dynamics of the biofilm, there can be a lot more improvements on what that would look like. And then I wanted to finish with some takeaway messages. So one of the things that we really like to talk to you is that to tell you is that the Lagrangian particle tracking that we do is really easy, and can really give you some very nice insights. We definitely encourage people to look at the website and see if they're interested, see what it takes. What we find currently is that due to different physical and biological dynamics, these particles can sink at the moment to significant depths. So that is interesting. And these oscillations and frequencies are something to be studied further. And so I wanted to conclude also with this nice simulation of the Equatorial Pacific, where we can see the smallest particles, they start sinking rapidly, and therefore they stay in this location, whereas the larger particles, they get advected with the currents, and you can really see at the end of the simulation here the equatorial countercurrent dragging some of these larger particles back towards the east. We hope you enjoyed our presentation, and we would be interested to hear your further questions and ideas.